All right, let's go ahead and take a look at an implementation here. So I've already loaded these packages, Tidyverse, Tidy Models, VIP, and I loaded my AIMS data here and I already split it into a training and test set. So recall in the last module, we learned about regularized regression. And if you remember, we can use this linear reg model, and we just changed the values of mixture, which is going to tell, basically allow us to specify, do we want a ridge model, which is 0? Do you want a lasso model, which would be 1? Or do you want something in between, such as a equal combination of lasso and ridge, which we call an elastic net, right? So I could set that value, and then I could choose some penalty value that I want to apply. So let's say 2,500. And all this should look familiar. All we're doing is a little bit of feature engineering here. We create our k-fold objects here to do a 5-fold cross-validation procedure. Now we add our model and our recipe to a workflow object, and then fit that workflow object to our k-folds, and then collect some metrics and take a look at. So we can go ahead and run this, and we'll see that we will get our average RMSE for this model when we have, this is a ridge model with a penalty of 2,500. Well, we may say, okay, well, that's great, but is that the right value for our penalty? Well, I don't know. Let's go ahead and change this to 1,000. And we can go ahead and rerun that, wait until we get the results. We could say, okay, how does that change? All right, okay. And we would probably have to write that down because I've already forgotten what I got on the last model. And I may say, well, okay, maybe a ridge isn't the right model. Maybe it's a lasso model. So let's go ahead and change that. We'll keep 1,000 as our penalty. And we can run this, and we'll get our result, and we see a different value again. And I may say, well, maybe now this penalty is not the right penalty value for a lasso, and I need to change that. And I can just keep going through this process, and you can see how it's cumbersome. It's not efficient. I'm just kind of taking guesses at what I should be testing out, running it. I got to record the values to figure out what is the best performing model. Well, we can do this in a much more efficient and smart way. So how do we do that? Well, let's go ahead. This time we're going to create a linear regression model object. It's going to be a regularized model, but we're not going to preset the values for mixture or penalty. Okay, we're just going to put in this function here, this tune function, and what that does is it basically says, hey, look, this is a placeholder. We're not going to preset these values. We're going to actually supply different combination of values to fill in later on. Okay, so this will create our regularized regression model object that's ready to be tuned. Okay, so we can go ahead and run that. Now, what are the values that we want to actually tune these hyperparameters across? Well, to do that, we need to create what's called our grid. It's our hyperparameter grid that we're going to search across and do a grid search with. Okay, so here, what I can do is I can use this grid regular function, and this is going to create a grid that has certain values for certain hyperparameters. Okay, well, how do we get these values? Well, over time, as you run more models, you get a little bit more familiar with what values should be looked at for different hyperparameter settings. But we're new, we're just getting started, so we don't have that knowledge. So instead, there are some nice convenient functions provided by the Tidy Models package that will basically provide smart values to assess, right? So with mixture, if within grid regular, if we just apply mixture, right? This is a function for our mixture hyperparameter here. And we can apply penalty, and that is going to be values to be used for this penalty hyperparameter. Okay, so I don't specify anything, and that's because these functions have default values that are considered smart to search across. And what I could supply is say, hey, look, I want to search across five values of each of these hyperparameters. right? And that's going to create a combination of these 5 different values. So we can see in our grid output here, for mixture, I've got values 0, 0.25, 0.5, 0.75, and 1. And then that repeats, right? So those are the 5 values for mixture that we're going to look at. 0, 0.25, 0.5, 0.75, and 1. And then we've also identified 5 different values for penalty. And so what we do is we get what we call the Cartesian grid or Cartesian product, where it's 5 values of mixtures, 5 values for our penalty, and we take the combinations of each of those. That results in 5 times 5, 25 different combination of hyperparameter values to look across. Okay. Now, one thing to note is we can actually override values if we wanted to. For example, mixture just has good default values, but penalty, this is something that we could actually change over time. And it's not uncommon to increase the range from the default penalty values. And I could do that, and I could just say penalty and then pass this vector of saying ranging from -10 to 5. And now maybe I want to look at 10 values for each of these hyperparameter settings. So let's go ahead and run this. And what we see is we get 10 different values for mixture, and we get 10 different values for penalty ranging from -10 to 5. There's actually a log transformation going on with those, but don't worry about that. And so that means we have 10 values of mixture, 10 values of mixture, 10 values of penalty. 10 times 10 equals 100 different combination of hyperparameter values to search across, right? And we can see that in this data frame, we have 100. All right, so now that we have a model with hyperparameter value placeholders, and we've got our grid search here that we can look across. In this case, it's 100 different hyperparameter combinations. Now what we can do is go ahead and we can train or perform our grid search. So how do we do that? Well, we create a workflow object again. We're going to add our recipe that we created earlier. We're going to add our model. Now this model right here is actually this model from right here where we have our placeholders for our hyperparameter values. And then what we do is we say we're going to tune this grid, and we're going to use our k-fold objects so that we can do our cross-validation procedure. And we're going to pass it the grid, our search grid that we want to search across, which is this one, is the last one I had created. And now when I run this, what's going to happen is we're going to train 100 different models, and each model we're going to use our k-fold cross-validation procedure. And then at the end, we're going to collect our results, and we'll see which model and which hyperparameter values perform best. All right, so we're done. If you ran this on your side, you would have noticed that it took a little while to run. Well, that's because we are actually running 100 different combination of hyperparameter values, and each time we're doing a cross-fold or a k-fold cross-validation procedure, right? So we're doing a lot of stuff here, and that does increase the computational time. But what we get in return now, when we actually collect our metrics, we're going to have our cross-validated RMSE here in order, or sorted in order from lowest to highest. And we can see that we have our penalty and our mixture hyperparameter values. So here we see that we actually have like the first 9 different models here. They all perform the same, right? They all achieve this 31,373 RMSE value. And that's using these different hyperparameter values, right? But if we were to kind of scroll through this, we're going to see that other hyperparameter values have an increase, right? Right here, we jump from 31,449 up to 64,000, right? And here we have 79. So actually, maybe these are not assorted. Let's go ahead. I'm going to arrange in ascending order on the mean. There we go. So now what we can see is the first 9 have this value, and then we start increasing. Well, one thing a common characteristic that we see here is the best performing models, all these that get the same low RMSE, are all using a ridge model. Our mixture is all equal to 0. Right? So it almost looks like, regardless of the value of our penalty, as our penalty increases, there's not a big impact, but using a ridge model seems pretty influential here. And as we increase from a ridge model into an elastic net into a lasso, right? We can even look towards the end here where we have very high RMSEs. We have our lasso model or elastic nets where it's a high ratio of a lasso penalty versus a ridge penalty. So this kind of indicates that, hey, look, a ridge model looks to be performing well. All right, so we performed our grid search and we saw that we have these certain hyperparameter values that seem to perform quite well. Now there's some convenient functions that we can use to look at our results. One of them is this auto plot where we pass it our tuning results here. And auto plot is going to plot our generalized errors based off of the amount of regularization, which is the penalty values, and the proportion of lasso, which is this a ridge, is it a lasso or elastic net? All right, so now we can see here that we have a lot of models that are performing quite, consistently and low across all these different values of regularization. But it looks like whether or not it's a ridge or not a ridge is the largest determining hyperparameter, right? But once we do get our penalty, our regularization penalty, quite large, we see all of a sudden a big increase in the RMSE, right? Now another helper function that we could use is a select best. Select best based off of some metric here, we're going to use RMSE. And what this does is it will actually identify the hyperparameter values that provide the lowest, in this case, RMSE, or the best performing model. So we can extract those hyperparameter values that we want. All right, so once we've done this, and let's say we've assessed our results and we're quite happy with them, then what we can do is finalize our model. So finalizing our model just means, first thing we want to do is select our best performing hyperparameter values here. And so now what I'm going to do is I'm going to take my workflow, add my recipe, add my model as before, and then use this finalize workflow function and pass it these best hyperparameters. Right? So we're not training our model, but we're creating a final workflow object that has our pre-processing steps, and then it has our final model with those hyperparameters that performed best in our grid search. Okay, so now what we can do is we can use this workflow object to maybe fit a model on new data, or maybe we want to go ahead and fit it on all the training data and assess the most influential features, which we could do that with this code here. And now we get our plot that we've seen several times in previous lessons that actually plots those features that are most influential in this particular model.